Okay, hi everyone. We're going to talk today about BlueBorne. Maybe you've heard of it. It's a research that we have done in the last year. My name is Seri. I'm the head of research at Armis.
And I'm Greg. I also work at Armis.
And Armis, the company we work in, is an agentless IoT security company that allows business to discover, profile, sanction the devices in their environment. And since IoT devices usually communicate not only in Wi-Fi but in other protocols, we came across researching Bluetooth specifically to understand it and to better develop security mechanisms for it in our system. So in that aspect, when we were researching Bluetooth, we came across a wide variety of vulnerabilities in Bluetooth in different operating systems. This actually is somewhat of a new attack vector in a sense that it really allows a wide variety of attacks to be performed against a wide variety of operating systems. It affects, well, it's used to affect, but it still affects a large number of devices, around 5.3 billion devices. Like I said, it's a set of vulnerabilities. It's 8 vulnerabilities, and 4 of them are critical vulnerabilities because it allows remote code execution. It affects Android, Windows, Linux, and iOS. And it is most severe or serious Bluetooth vulnerabilities in these stacks in the last 10 years or so. This is primarily because these attacks do not require any user interaction or authentication. The devices don't need to be paired for the attack to take place. And also because it enables a wide variety of vulnerabilities and options for an attacker, either the remote code execution vulnerabilities, there are 4 of these, the man-in-the-middle vulnerabilities that are something similar to the Wi-Fi pineapple, only over Bluetooth, and information leaks that are also very important for attackers in order to bypass mitigations, and we're going to talk about this in this talk specifically as well. Like you can see in this graph here, it's very visually plain and simple. All around the Bluetooth stack, we found vulnerabilities. These are not the same vulnerabilities in each operating system. It affects each Bluetooth stack a bit differently. But we have the 4 RCEs. There is one in the L2 coupler. I don't know if it can be actually detected, but in Linux, there are 2 RCE vulnerabilities in Android, one in the BNEP service and one in the PAN profile. We have one iOS RCE in a proprietary protocol of Apple that's called Leap, and 2 man-in-the-middle vulnerabilities, one affecting Android and one in Windows, that are also in the PAN profile, and 2 information leaks in the SDP service that we're also going to describe. Those affect Linux and Android. Today, specifically, we're going to talk about the Android vulnerabilities and the exploitation of the RCE vulnerability in Android. So we're going to start a bit with background on Bluetooth and what is needed to understand to exploit these vulnerabilities. And then we're going to talk about the process of exploitation for the Android RCE. And we're going to describe 2 vulnerabilities that we needed to achieve this. One is the SDP information leak vulnerability that is used to bypass mitigation, bypass ASLR. And the second one is the BNEP, that is the service that we're going to discuss in the Bluetooth stack, which we found RC vulnerability and how we exploited it and what the process needed. And lastly, if all goes well and the setup here is, and the gods are with us, we're going to do a live demo showing this as well. So I want to start first by tagging an issue that has some common misconceptions about it, and that is discoverability. And you might have heard of this concept. This is a term in Bluetooth. It's discoverable. Bluetooth has a mode, Bluetooth devices have a mode in which they can be found by other devices around them. That is discoverable mode. And it is usually thought of that a MAC address of a Bluetooth device can only be found when they are in this mode. This is actually not true. And there have been prior work. This is not something that we made up, that we invented, but there have been prior work showing how MAC address of Bluetooth devices can be found. It starts by the fact that Bluetooth devices transmit part of the MAC, the LAP, over the air each time they send packets. And once you sniff one packet of a Bluetooth packet, you can brute force another part of the MAC pretty easily because there are only 30 options. And actually, you only need 2 parts of the MAC in order to communicate with the Bluetooth device. There's actually an open source tool that does exactly this. It's called Ubertooth, and the research around it has done a lot of work in demystifying the discoverability and generally demystifying the lower layers of Bluetooth, the PHYs, the link layers. This tool just allows automatically for attackers to find undiscovered MACs and MACs that are of Bluetooth devices that are not in discoverable mode. So this is one approach for an attacker in order to find a MAC address of a Bluetooth device. Another one is just to use standard Bluetooth chips that you have in your devices with some firmware modifications. This was done in the past. It does require some research to do this today because the chips are different, but it can be done. And there is another very simple trick that can be used by attackers, and that is the fact that today a lot of chips, wireless communication chips, use Wi-Fi and Bluetooth in the same chip, and OEMs tend to have the MAC addresses of Wi-Fi and Bluetooth adjacent to one another. So if you are going into monitor mode in Wi-Fi, you can find the Wi-Fi MAC address that is plain text over the air, and an adjacent MAC address of the Bluetooth device just by going plus or minus 1 of that device. On top of all of this, discoverability is not a prerequisite in order to establish a connection. A Bluetooth device is always listening to incoming connections, even if it's not in discoverable mode. So having found the MAC address using one of these techniques, an attacker can then go on and attack a device or communicate with a device that is not in discoverable mode. Bluetooth is complicated. It's actually 2,800 pages long, the spec alone. Some of the pages look like that. This specific page shows the 4 layers of fragmentation that exist in the lower layers of Bluetooth. This is before the application layer. Shows there are other fragmentations above it. It does really a poor job in the sense that it re-implements a lot of features over and over again. There is no reason to have 4 layers of fragmentation. One is pretty enough. This flowchart here only shows what does a Bluetooth stack look like. It's a big chunk of protocols combined together. It is actually a complete redo of 7-layer models or the TCP/IP models. It doesn't use standard protocols. It implements its own for each step in the way. The green one on the middle there is the L2 cap layer, which is the Bluetooth equivalent of TCP. It is used to open connections that have some quality of service in them to specific services, and those are the layer above L2 cap. As you can see, it's a very wide attack surface. A lot of services are run inside each stack that can be targeted. And specifically, we wanted to start with the one that is marked there in the red. That's the SDP service. SDP is Bluetooth Service Discovery Protocol. It is used to discover what other services other than SDP are listening on a specific device. So by design, it has no authentication because it is the first step in communicating between devices to find what other services are available inside the stack. The way it works is very simple. You have a client, this is one of the devices, and a server, that is the other, and the client will send requests to the server, searching for services on that server, or requesting more info on that server, and the server will then respond with details on that service. In the case that the response of the server is larger than a single Bluetooth packet, yet another fragmentation exists in SDP. SDP continuation is the name of this fragmentation mechanism that is implemented in SDP on top of other fragmentation layers that are below it. The way it works is actually different than usual fragmentation, because in this case, the client needs to send the initial request, and then in order to receive more fragments, it needs to send again the request over and over again until he receives all the fragments back from the server. What you can see there is that the server appends a continuation state, that's the const state, to each of the responses it sends. And that continuation state is actually the internal state of the server as to where he is inside the full response that he wants to send. The client will then add the continuation state to each request he sends in order to get another fragment. And that process will go on and on until the final response will be received without a continuation state. The question that we ask when we look at this graph is what happens if the client changes the service that he's searching for, that is the unique UID in his request, between one request and a second request before the continuation exchange is over. And this exact state confusion is what led us to find this vulnerability in Android, the information leak over SDP. What you can see here is there is the number of response handles, and this is the total size of the response that needs to be returned. Each time the request is processed, this is the function that processes a specific request. Each time it is processed, the number of the full response is generated again. The continuation offset here is where we are, is the current continuation offset. And that's the internal state of the server. That's the const state that we saw before. RAM handles holds the number of remaining bytes or remaining data that should be exchanged, sent back in the exchange. So if we change the UID that is being searched, that is being requesting during a continuation exchange, the state confusion can be achieved, and the RAM handles can be underflowed because number of response handles would be changed. So the code assumes that it had one value, and then it has another value, and then that can underflow. Once that underflow is achieved, there is the full response buffer, that's the RSP handles, and that can be read out of bounds, and it's actually allocated on the stack. So it will look something like this. The client would send an initial request using a unique UID. The server would send a response, reading from the RSP handles buffer. Then the client would change the request he is looking for, but he would use the same continuation state. He won't break the protocol in the sense, he won't change the continuation state, but he will ask for another UID. So that would lead to the underflow of RAM handles that would allow to read out of bounds from the RSP handles into the stack that inside it is allocated. That stack would contain pointers that can be used by an attacker to bypass ASLR, because these pointers can point to libc variables, libc functions, or to the global variables from which the ASLR basis can be derived and completely bypass ASLR. Now I want to talk specifically about Android's own Bluetooth stack and how what services does it implement and what options exist for the attacker specifically in Android. So Android has its own Bluetooth stack since version 4.2. And this is called BlueBorne or Fluoroid in some versions. So it doesn't use the Linux Bluetooth stack that is called Blues at all since version 4.2. It is not run inside the kernel. It runs in user space, but it runs on a Zygote. And it is an exceptionally privileged process because it has a lot of functions to do inside the system, as it is a Bluetooth stack that needs to implement a lot of functions. If we take a look specifically in Android, what services does an Android smartphone, in this example, a Pixel, what services in Bluetooth does it serve? And there, as you can see, there are quite a lot of these, and they sound interesting as well. They host a lot of features in the Bluetooth stack. So that big chunk of services that we saw before, this actually does exist, or a lot of it exists inside Android as well. So the attack surface is not small at all. I'm going to try and prepare the demo, and Greg now is going to talk to you about BNEP, which is one of the services, and the RC vulnerability we found in it.
Okay. So this is the SDP output for Google Pixel, as Ben has said, and it basically shows all the services that are available for any peer to connect to on that Pixel. And one of them caught our eye. It's called BNAP. Really, we didn't know what it was. But what it actually is, it's that old technology of Bluetooth tethering of letting you use an internet connection to share an internet connection over Bluetooth. It surprisingly still works today, even though it's like 1 megabit. I don't know, nobody uses it, but it still works. Basically, how it works is that there is a topology of what they call a personal area network, a PAN, and there is an app, which is the access point, which in this case would be, say, an Android phone, and there are clients, they're called PAN-Use. They can connect to that network and have and share that internet connection. Basically, the way the protocol works is simply Ethernet packets with IP packets in them encapsulated inside what's called a BNAP, the BNAP protocol. And basically the way it is, it's just Ethernet packets and some extra control data over L2CAP, which, as we've said previously, is like the TCP of Bluetooth. So basically it's like a tunnel over a network tunnel over Bluetooth. Looking at this code, the very first function that receives those messages over L2CAP, again, L2CAP is like TCP, so there is a listening TCP server, and this is the handler for the packets. To get to this point, no authentication is required whatsoever. Basically, at this stage, the state of the BNAP service can be changed to connected. But while it's not connected, it's supposed to be possible to send a setup message or other control messages. And to send them, obviously, authentication isn't yet required. It may be required later, but now it isn't. So basically, in that very first function, which is quite big, there is this specific flow, which leads to an off-by-1 heap overflow, where the structure size of p-pending data there is 8 bytes. So it's an overflow of 8 bytes on the heap every time this flow runs. That's really weird. I mean, it means this code never executed, not during testing, because it would have crashed the service. So basically, it's possible to send the very first packet as this packet, that overflow trigger there. Basically, it passes all the checks based on the state being that it's not connected, and then there are some other fields like type and control type. Basically, they lead to that memcopy over there. What's especially convenient about this particular vulnerability is that except for the memcopy, the attacker also controls the allocation size in that malloc over there, because RAM-len is basically just the length of the packet that the attacker sent. So basically, we have an 8-byte heap overflow where the attacker selects the size of the buffer on the heap that is being overflown. So that's very convenient. Also, we thought, well, an 8-byte heap overflow, maybe that's unexploitable. And then, indeed, we've looked a bit deeper, and we found that that Android stack has a thing called an allocation tracker that basically adds an 8-byte long canary to every heap buffer. So we thought maybe that's unexploitable now. But digging a little deeper, it's possible to see that it's just compiled out on non-debug builds. So, okay. At that point, we just started sending that trigger buffer, that overflow buffer, just hundreds of times. And it's possible to see the crashes in ADB logcat, which is the standard Android development logging system. Interestingly, you can see those crashes even if the phone is not rooted, and that's a privileged process. Okay. So what we've noticed about those crashes is that basically they're just repetitions. Like all crashes fall into a set of 6 or 7 different crashes. And we've looked at some of them. One of them, again, caught our eye. It occurs naturally if you just send those crashes. If you do the crashes again and again, it occurs about 10% of the time. The instruction pointer there in the source code, which again, the Bluetooth stack is Android, it's open source. It points to this function, BTU HCI message process. And looking there, we've seen a bunch of red flags. So first, what we understood this function does, this function handles all the HCI messages. HCI, it's the protocol between the hardware Bluetooth controller and the higher level OS stack. So basically, every message that comes from the hardware, or received message comes from the hardware to the stack, passes right through here. For some reason, they decided to add this post to task, no good, horrible hack type of message. Actually, well, we understood what the reason is. It's sort of a thread synchronization thing, where they want to pass tasks as callbacks into this thread, because this thread does most of the Bluetooth data structure stuff. So this is kind of a synchronization mechanism. So I don't think they can easily remove this, but I don't know. The crash itself that was in the crash log is basically on that first dereference of pmessage there, pmessage event. In our case, pmessage was all 41s, like in our overflow. But what's going to happen if we can point that somewhere with a fake, horrible hack type message, then we can take control of that callback over there. So basically what this does, again, is it takes that pmessage, it checks the event type to be horrible hack, and then it takes 4 bytes out of the message as a function pointer and calls it with the message itself as a parameter. So at this point, it still wasn't clear what exactly are we overflowing that causes that flow to happen, so I'm going to explain it now. This function that I've shown you before, BTU HCI message process, is called from a function above it that dequeues an HCI message from some queue. That queue probably comes from another thread that reads it from the hardware. And basically, when we looked into it a bit more, what we've seen is that all the queues and all the lists in this Bluetooth stack, in this code base, are based on a list node structure, which is just a node in a linked list, which is 8 bytes long. And indeed, if you recall, our trigger overflow buffer was also 8 bytes long. And on Android, they use the JMalloc heap. And what it does, very conveniently for us now, is it places all buffers of a similar size in the same space. Also, if the allocations happen on the same thread, it places them on the same place, and this is the case. So basically what happened with our overflow is that we've overflown one of the list nodes that belong to the incoming HCI message queue that wasn't handled yet, and the minute it was handled, it got passed to that function, the HCI message process function, and there we crashed. So basically, now I'm going to outline what the strategy for the exploit is going to be. So we have already the ASLR bypass, so that's good for us. We can know address bases of libc functions, which we'll use as the callback, and some other things. Now what we want to do is write a payload into memory, which will be that horrible hack message structure. Somewhere in memory with a deterministic address, which will become possible because we have bypassed SLR. The callback will set it to be simply the system function from libc, which again we know the address from the SLR bypass. And the system function will receive the p-message itself. So we'll make the p-message payload dual purpose so that it will serve both as the horrible hack message and a bash script to run a system. And the next thing we do is we send our overflow trigger again until we overflow the HCI list node, and hopefully it gets processed by the processing function, and our bash script will be executed. Now, as I've said before, very conveniently, this crash happens naturally 10% of the time, and being a service on Android, it runs under something called Zygote that simply restarts the service if it crashes. So we don't really need to do any heap shaping to improve our odds. It will just, the attack takes more time, but we did it just to shorten the attack. So what that payload actually looks like, above you can see that what we want is that data pointer in the list node to point right in the leftmost byte of that buffer. And the way we structure it is that the first 8 bytes are of type BT header, which is that structure that contains the event field that we need to set to 17, 17 being that horrible hack event. The way the code checks it, it checks only the lower byte. So we use the higher byte of that event as quotes in order to make this whole thing a valid bash script. So the first 8 bytes are what I explained, and next is the callback at offset number 8, and the rest of the payload is simply structured to allow arbitrary bash commands to be executed. Yeah. Now, what happens in that function now, again, is that the first 2 bytes of our payload are parsed as that event field. That mask over there simply checks only the lower byte, and the case for no good horrible hack is 17. So if those first 2 bytes have 17 as the lower byte, our callback will be executed. This whole payload is passed into the callback, which is system, and it is a valid bash script. Okay, so one of the last things that is remaining is where do we place that payload in memory so that we know its address deterministically. And what turns out is that in Bluetooth, there is such a thing called the remote device name. Every device has a name, and we make a connection to the target as a peer, so we also have a name. And the name is exchanged during the basic ACL connection. That's like the basic Bluetooth connection between 2 Bluetooth controllers. And once the connection is established, our name is written into the memory of the target Bluetooth stack, and it just so happens that there it's in a global variable. And from the ASLR info leak, we know the base of the BSS section, which is where all the global variables are stored. And that means that the name, our device name, will have a deterministic offset in memory once we know the ASLR base. So on an attacker machine, say on Linux, it's really easy to change our own device name. So we change the device name to that payload. Conveniently, in Bluetooth, the device name is 248 bytes long. It just cannot contain any null bytes. Okay, we'll live with that. So now we have almost all parts of the attack. This is something that we're not going to elaborate upon due to lack of time, but we shape the heap slightly, as I said, in order to increase the odds. What we want the heap to look like, and let me just digress a second into what is it that you see here. This is what should be a run on the JMalloc heap. A run is basically that physical area where objects of the same size that are allocated on the same thread will be placed. So what we want is the leftmost hole on that run to be 8 bytes long, so our overflow buffer will be allocated there. And immediately after that, we want a list node that belongs to the HCI message queue to be there, so that when that hole is allocated and the overflow happens, it overflows this list node. It can be any list node that belongs to that queue as long as it is unhandled yet. And basically, if we do our attack over and over again, either we crash by overflowing something else, or this and lead to our execution of system. Basically, to explain shortly what's going on in this heap shaping is that what's usually going on in the Bluetooth stack is nothing, because no one uses it so much. And if someone is using it and we crash it once, then no one is using it at the moment, basically. So the heap is really deterministic. It will take some time until something will happen again. And what we do is eventually we force the BNAP service, something else in the BNAP service, to send us lots of response messages in a certain way and order. These responses will cause allocations and freeze of 8-byte objects. And again, without saying exactly how it works, we can make it shape the heap in a way that increases our odds significantly. So again, let's reiterate on how it works. First of all, we do the info leak and we learn the address bases of ASLR. Now we're going to establish a connection with our payload device name and write that horrible hack message into memory. And now we're going to do that optional heap shaping. And immediately after, we'll start sending our overflow triggers in a loop with that crafted list node that points to the horrible hack message. until either we crash and then get restarted, or we succeed and we run a bash command. Empirically, this sort of works 50% of the time on the device we tested for like each attempt. So that means that including the restarts, it would take like a minute for the attack to succeed at most. Okay, and we wanted to show that the source code for the exploit will be available very shortly on GitHub. And again, there will be a blog post explaining in a lot more detail what we've shown in this presentation. And of course, there is the full white paper that we've published in September that contains the description of all the vulnerabilities, not only the Android ones. What it doesn't have is the exploitation, which is the new thing we're showing today. And now we'll try to do a demo, hopefully.
Yeah. So we'll set it up for a second, then we'll explain what's going to happen. What we have is the attacker, the laptop, in this instance, and he would attack the Google Pixel that we're going to show. The way it's going to work is, first he will establish a Bluetooth connection. Using the SDP vulnerability, the information leak, and the BNIP RC vulnerability, he would achieve code execution. And the payload, the bash commands themselves that are going to be run is just a netcat connection over the internet back to the attacker. So once we have the shell command over the TCP connection, we no longer need the Bluetooth connection, and we can run whatever commands we want. And we are running inside the Bluetooth stack, BlueBorne. And what is important to note is that the Bluetooth stack is exceptionally privileged. I'm going to show a few things that can be done once you are inside it. So on the left here on the top is the terminal for the attack, and that, you can just focus on the pixel for now. Okay. Right now, nothing is apparent, and hopefully it will work. Okay, let's go. So it starts by doing the memory leak. It connects to BNIP, and then it will do the heap shaping and triggering of the overflow, and it worked. Yay. So we are inside the context running of the Bluetooth stack running a bash command line. And we can see that the user is Bluetooth. That's the user of the Bluetooth stack, and it has a lot of privileges inside the Bluetooth, inside Android. All of these groups that it is part of. For example, you can see the file system. I don't know if you actually can see the text there, but trust me, it is. And we can also view, for example, images that you have inside your that you photographed with your Android phone. And of course, we can run whatever executable exists inside the Android, like the netcat that we used to connect back to the attacker. One interesting thing that exists inside the Bluetooth stack is its ability to emulate a mouse, to emulate an HID device. This is because you want the ability to connect a Bluetooth mouse to your phone or a keyboard. And for that reason, the Bluetooth stack has privileges to interact with the DevU HID, which is a device, the kernel device for playing HID events. So we take abuse of that fact, and we upload a script, a bash script that just plays recorded HID events that allows us to have control of a mouse inside the pixel. So here it is, here it goes on, and you can see that mouse. I hope that you can see that mouse cursor over there. And that, of course, emulates whatever a user can do with a phone, now the attacker can do. On top of that, you have Android intents, and that's an IPC mechanism in Android to send all kind of messages. So the Bluetooth stack can also send these intents. For example, you can send an intent that wishes to open the camera. So this is what I've done now. Right, so, oh, here it is. And we can switch to the front camera and take a picture of Greg, or his camera at least. Yeah, here's the hand of him. And we can open the lock screen. In this case, it is not password protected. And we can go to the Play Store and install our own malware of choosing. And do whatever actions the user wants to do. We can go to the settings. You understand the gist. It is pwned. Thank you. So we have another something that I think we have a bit time to do, and that's second stage of the attack. What happens if an attacker wants to create kind of a botnet or start spreading the attack from one device to another over Bluetooth? From that point, the attack would not be limited. Would no longer be limited to the Bluetooth range because this patient zero, the device that has been attacked, can then go around the world and attack other devices. So we wanted to test out how something like this can be achieved. And the idea is, first, we have the shell command that we saw right now that the attacker gained on the Pixel phone. And from that point, he wants to run his own code that allows him to control the Bluetooth of the Android phone in order to use it to attack other devices. The HCI connection that exists between the controller and the Bluetooth stack, the BlueBorne, is actually a socket or a serial file descriptor that is open inside BlueBorne. And since our shell, the attacker's shell, is a child of that process, he inherits the file descriptors, and he can use that HCI connection. We use simple Java code to open another TCP connection. And we use the file descriptor of the HCI as now the file descriptor that goes directly to the Java process and is routed over this TCP connection to the attacker. So now the attacker can control the Bluetooth controller on the patient zero device, since it can send over this TCP connection whatever HCI commands he'd like. And we're going to demo this now. It's pretty new. I really hope it works. But eventually, the effect is attacking another device, in this example, a smartwatch. And the demo we're going to do next is the next stage, the patient N, if you would like. We won't use the Android vulnerabilities. We're going to use the Linux vulnerabilities that we haven't talked about, but it is in the technical white paper. And do some tricks with that as well. So over here, we have on the top the Android shell, with our bash command that does all kind of trickier for us. So the first step is to stop the current Bluetooth stack in Android because we want to have the sole control over the HCI socket. So we're going to do that. That's K there, that's the command that stops the Bluetooth stack. Now we're going to start another socket, the TCP socket, that is going to control this HCI socket. And then the Android will attack over its Bluetooth connection, it will attack the smartwatch. So we will just launch the Java code that does the rerouting of the HCI, and hopefully it would work. Okay, so you can see there, okay, that's great. You can see that the attack started. I'm not going really to explain specifically this Linux vulnerability, but it achieves code execution via Bluetooth as well. And now we can drop into shell. We are running as root, as we're going to see in a minute, inside the Linux system. And we have one more trick up our sleeve, and that is the smartwatch actually has an X server that does the graphics for the watch. Yeah, as you can see, the watch is still fully functional. And we are running our code inside of it. So we can use the X server of the watch to display whatever we would like on its server once we have our control. And like you can see, there is now the BlueBorne logo all over that watch. That's just our own laughing matter. So lastly, of course, we have full control, and we can reboot this smartwatch just for the sake of it being without BlueBorne on it. I think that is it. Do you have any questions? I don't know if we have some time, but maybe 5 minutes. With the microphone?
We have time, yeah.
Okay, let's start and see if we can hear you.
How hard do you think the Android application would be without a horrible hack?
I don't think it would be that much different. There are all kind of callback functions in the memory, in the heap of an Android, so it would take considerable work to remove these kind of callbacks. JMalloc itself can also be used. Like it does. There are techniques to attack JMalloc specifically. They are much more difficult than the horrible hack, but it's just something that made our life much easier. But of course, heap attacks, heap overflows. There are infinite ways in order to gain code execution when you do that.
Really, the big advantage there was that in the BNAP vulnerability, it was possible to select the size of the buffer. So we just started with 8 bytes, but we could choose any size and thus target any object in the entire system. If any of them had a callback, it would have been almost the same, as long as it's been like on the first 8 bytes. Okay.
So my question would be, could you also use BNAP to establish a TCP connection to the own phone?
Yeah.
Right, because you use now a separate channel, but could you use BNAP as well?
Right on the money. It's something that we considered when we did the exploitation. It did require us to restore the heap a bit and have the code of the Bluetooth stack keep on running. But of course, instead of going to libc system, what we could also have done, and it's not very difficult, is develop a simple warp chain that will load our code from a file or just over the internet or over whatever, and use mprotect to run our own code. And then, of course, we can also use, once the stack is stabilized, we can use BNAP and we can use a TCP connection over that interface as well. Yes.
Thanks.
Sure.
We have another?
Yeah.
You mentioned that there is like a 50-50% chance of success if nothing uses Bluetooth. How successful is the exploit if the target is using, for instance, a Bluetooth headphone to listen to music or something like that?
On the first attempt, it will fail, and on the second, it will probably succeed with a 50% probability, because once we crash the service, everything that's been done will stop, and the user won't restart it in time before we manage to run our thing.
I want to add to that. The fact is, we didn't spend a lot of time on the heap shaping because this is not a weaponized tool. This is just for our fun and a bit of profit.
Okay, thank you.
But so any heap shaping that is more sophisticated than what you have done could have resulted in better chances than that.
Yeah, the exploit that we will show on GitHub is really an exploit only for this particular build. It's not weaponized or anything. So yeah, it's limited.
It's not very hard to make it more wide. There are just a couple of symbols that needs to be adjusted per build, the libc system. Such, yeah.
The BlueDroid related vulnerabilities you discovered look pretty much a clever backdoor to me. Or were you just that lucky, really?
It didn't look like a backdoor, no, because too many factors played. It was pretty easy, as you've seen, but I think that's a matter of
simplification.
Yeah, maybe a little bit of luck, because I really think it's just because there is so much code and it is so untested that this was there.
I think part of the reason is that we didn't talk about this at all right now, but it is in the technical white paper that we wrote. There is an assumption in the code that high-level services like BNAP should be only in use with paired devices, with devices that you have been paired with. And we found a way to bypass authentication, specifically in Android and Windows as well, that this vulnerability actually doesn't require it, but other vulnerabilities in higher-level services does require some authentication bypass in order to trigger them. So I think maybe Android thinks their code is protected by this false safety mechanism, and maybe that's the reason they haven't gone to all the lengths to make their code a bit better.
Do you know why this BlueDroid process is granted with read SMS permission?
Yeah, I actually looked at that and I didn't know. Maybe there's a feature to just read. Why did it have read SMS functionality?
If I'm not mistaken, once back in the early 2000s, it was possible to to use a Bluetooth headset. Well, you could use it for calls, and I think there was some feature that would have allowed you to use it for text as well, and for sharing your contacts. It can also transfer files. That's why it's accessible to all your pictures and everything. Bluetooth, like, think of any Bluetooth functionality or device that you've ever seen. So this one daemon has all those privileges, which, as we've shown, are effectively what the user can do on the device. The only thing it doesn't have is the ability to root the phone. Except for,
Unfortunately.
yeah.
Hi. How much time did you spend not considering the remote execution vulnerabilities on researching this Bluetooth problem, this Bluetooth vulnerability?
It's something that we've been doing in the last year, but we published in September, and back in April, it was already in the process of doing the disclosure process. I think maybe 3 months, something like that. Not a significant time.
I'm just asking because you wrote in your publication that since Bluetooth 2.1 specification, which was in 2007, I think, there was a decade, 10 years, and nobody came up with this serious vulnerability. Is it not probable that someone already found these vulnerabilities but didn't publish it, and it was exploited?
Yeah,
Of course.
of course, it's powerful. We don't have
Because
the knowledge.
10 years is such a long time for such a serious thing not to be discovered.
I think it's what our understanding of that is that Bluetooth is very complicated, and it made researchers and attackers stay away from it. They don't want to read 2,800 pages of spec to understand how to attack a device. So, and neither did we.
The reason we looked at Bluetooth is because what our company does is monitor, among other things, Bluetooth connections. So we already had to look at that.
Yeah, we
After
have
that,
to
yeah.
Okay, thank you.
Okay.
Is there anybody else with a question?
Right.
No? Well, in that case, thank you very much to Ben
Thank you very
and to
much.
Gregory.